Бо я буду робити тільки...
Добре, я вертаюсь. Да, секундочку.
Got it,
Зараз.
got it. Yes, now it's...
Who make a recording? Хтось записує.
Все працює. Починаємо
Yes.
працювати.
And now is the talk of Professor Zaidenberg, which this talk Gromov's ellipticity, old and new. Please, Professor.
Okay, thank you very much. It is my pleasure to be invited to participate in this conference and an honor. Why does not it work? Okay, actually I'm a newman in the Gromov ellipticity, starting to work on it recently, and all the remarks are welcome. I will not prove anything, but whatever I will advertise is all the proofs are available publicly. Two of them in preprints, all the other are published. Okay, so the origin of Gromov ellipticity lies in the Oka-Grauer principle. What is this principle? So this is a theorem which was initiated by Oka in 39 in the thesis of Grauer 57 and publication 58, and in the article of Forster Ramsport. And you can formulate it like this, that if you have a Stein complex manifold and a complex Lie group G, and you would like to classify principal G fiber bundles over S, that is fiber bonds with a structure group G, and the fiber principal, yes, so the fiber and the structure group is G, then the topological classification and holomorphic classifications are the same. This means two different assertions. If you take over S, I will stay with the simplest case when the fiber bundle is a vector bundle. So given a vector bundle, which is over a Stein complex manifold, but just a topological vector bundle, then in this case, G is GLN, then you can introduce a holomorphic structure on this vector bundle. That is, there exists another holomorphic vector bundle over the same base, which is topologically isomorphic to the given one. And this second assertion, that if you have two holomorphic vector bundles over S, which are isomorphic topologically as topological vector bundles, then there exists between them a holomorphic isomorphism. So this is very useful, actually, theorem. I use it when I wrote my PhD thesis for the families of Fredholm operators, and really very useful. So what is the role of complex Lie group here? What really the features of G, which is used in the proofs? There are two of them. A says that any continuous map from S to G, where S is still a Stein space, is homotopic to a holomorphic map via continuous maps. And B, if you are given a holomorphic map from the closure of a bounded convex domain in Cn, then you can approximate this map by the entire holomorphic map from the whole Cn to G. Okay. Now I turn to Gromov's influential paper of 89, which actually answers the following question. What should one know about a complex manifold X to be sure that you can replace G by X in this A and B? And this is A and B still hold. So for such a replacement, Gromov suggests two new notions. The first is of a spray, and the second is of ellipticity. So what is spray? A spray on a complex manifold X is a triple E, P, S, P, S small, where P is a projection of E to X of a holomorphic vector bundle on over X with zero section Z. And S is just a holomorphic map from E, from the total space to the base, which is, say, identical on the zero section. More precisely, if you take a point as X small in X capital, and the fiber EX, which is a vector space over this X, and with origin 0x, then S send this origin to the point X small. And this holds for any X small from X in X capital. That means that it coincides with a projection on the zero section. Otherwise, it is arbitrary. Now, what is important is the property of dominating for such S, for such spray. A spray is called dominating if the differential of S at the origin of the fiber. So you consider S restricted to the fiber E capital S small, X small of this. And then you consider the differential at the origin. This is a map of Cn, say, to X capital. Then it should be surjective onto the tangent space of X capital in this point small x. That means that you so you map every fiber to the variety so that the origin of the vector space is mapped to the point where the fiber is taken, and it maps dominantly. That means that covers a neighborhood, a classical neighborhood of this point. Okay, and this is somehow a family of such vector spaces and of such maps, a good family. Now, the second definition of ellipticity: X is elliptic if it admits a dominating spray, EPS. There are accompanying two notions. Locally elliptic, which actually participates in this paper without name, of Gromov. So this, I mean that Gromov did not give this term, locally elliptic, but locally elliptic means that you can choose an open covering of your space X, such that any member of this covering, UI, admits a dominating spray with such a relaxing of conditions that SI takes value not necessarily in UI, but in the whole X. But other conditions are fulfilled. So this is a local ellipticity, and the next notion was suggested. So this is localization in the term of the base of your spray. But there is another localization suggested by Forsnerich in the terms of the fiber. Instead of one vector space, you can choose a sequence of vector spaces. So this, I mean, sequence of vector bundles finite sequence of vector bundles over the same X. And then you consider for sprays on each of them, and the domination should be collective. That means that you consider the images of the tangent spaces as the origins for any of these bundles, and all of them are subspaces in the tangent space of X capital, and these subspaces should span this tangent space collectively. Okay, so it's evident that subellipticity is much weaker than ellipticity, but gives actually the same properties. So why the ellipticity is useful? There is a Gromov's H principle. There was several years before this article, very general monograph of Gromov about H principle for partial differential equations. And then he applied this to the Cauchy-Riemann system. And then in this paper of 89, it is proven that any elliptic complex manifold X capital verifies A and B. This is a manifestation of the more general H principle in the case of complex manifolds. More precisely, the theorem of Gromov says the following. If you have a Stein complex space and a complex manifold X, I recall you that Stein means that this your complex space S is a closed subspace of Cn, nothing else. And X, any complex manifold, then X is, which is elliptic. Then you have A, every continuous map from S to X is homotopic to a holomorphic once via continuous maps. And B, if you have a bounded convex domain in Cn and function holomorphic in a neighborhood of the closure, then it can be approximated on this closure by holomorphic maps of Cn to X. Okay, this is some complex version. Actually, you will. So actually, I have to say that this ellipticity, so the existence of dominating spray, A and B are, in a sense, are equivalent. So there are theorems that say that the inverse to this theorem. So Gromov in the same paper introduced the same notions in the algebraic category. That means that you just replace complex manifolds with algebraic smooth manifolds, holomorphic vector bundles, algebraic vector bundles, holomorphic maps, biregular maps, means morphisms, and so on. And there is a difference between two interpretations, and I will explain this difference later on. So in algebraic category, we have really this some equivalences that I will announce in a minute. But I have to say that the analogs in analytic category are known only when X itself is Stein. So the theorem says that for a smooth algebraic variety X, the following are equivalent. X is elliptic, X is locally elliptic, I'm sorry, and X is subelliptic. The first two properties were implicitly already in the paper of Gromov, and the equivalence subellipticity to ellipticity was published this year, some 33 years after the first. So for 33 years, that remained open question. So now I give an example, a class of varieties which are elliptic. This so-called flexible varieties, which appeared much later, and in the context of algebraic varieties. Consider the additive group of the complex numbers and assume that you have an algebraic variety X with an action of this group. Let us say smooth variety. The action means that you have a morphism GA times X to X satisfying the composition law. And consider the trivial vector bundle GA times X over X with a second projection of rank 1, because the fiber is GA, just the complex line. Then this triple, the P is a second projection and S is the morphism of action, is actually a spray. Of course, the image of each fiber is the orbit of the point on X under this action. And if X is multidimensional, it's never dominating because the orbit doesn't contain an open neighborhood of the point from this orbit. Okay, so now the definition. When the variety is flexible. So then a variety is flexible if it admits a collection of finite collection, say, of GA subgroups of the automorphism group. So this means GA actions, such that the velocity vectors of this action at each point span the tangent space of this point. So the number of vector fields may be much bigger than the dimension, but at least part of them is linearly independent of this rank, which is the dimension of X at any point. So such a variety is flexible. The examples, non-trivial examples of flexible varieties appeared. Any homogeneous variety of linear algebraic group is, of course, flexible, but non-trivial examples appeared in the first thesis of Gizatulin. There are surfaces, Stefan surfaces, which are not homogeneous for any linear algebraic group, but which are flexible. So theorem of which also can be seen at the beginning of the Gromov paper, while the flexibility was not there at this time, but it is implicitly there. So any flexible smooth affine variety is elliptic. And then you can introduce the notion of local flexibility, and then you can omit the word affine. Then you can deal with any algebraic variety. If it is flexible, then it is locally flexible, then it is elliptic, because ellipticity is a local property. For instance, the Danilevsky surface in C3, given by this equation, this is a smooth affine surface. It's flexible and hence elliptic. Then I give a series of examples of, there are many flexible, known flexible variety, all of them are elliptic, and this is a main source of examples, but actually flexibility is much stronger property than ellipticity. So a homogeneous space of a complex Lie group is elliptic in analytic sense, not necessarily in algebraic sense. If G is semi-simple linear algebraic group, then the homogeneous space G over H is elliptic in algebraic sense. As an example, C star, so the punched affine line, is elliptic in analytic sense, but not in algebraic sense. We don't need any image, non-constant image of C. The same holds for any projective elliptic curve. Projective elliptic curve is a complex Lie group, so elliptic in analytic sense. but it does not admit any morphism from C, regular morphism. Therefore, it is not elliptic in algebraic sense. So the trivial example C and Cn Rue's manifolds are elliptic in algebraic sense as algebraic manifolds. Gromov claimed, and that it proved, and that was then proved by many other authors, that if X is elliptic and you choose a closed analytic subvariety of codimension at least 2 in X, then removing this subvariety you do not affect ellipticity. So the complement is still elliptic. Therefore, you have many new examples just from those that I gave already. Then, of course, the localization principle by Gromov immediately implies that if your variety, algebraic variety, can be covered by the risky open subset isomorphic to the vector space Cn as a manifold, then you have an ellipticity. Any smooth projective rational surface verified this property. Any flag variety, G over P, where P is a parabolic subgroup of the linear algebraic group G, verifies. And moreover, complete spherical, in particular toric varieties, verify this property, can be covered. Then there's, I will stay on the properties of elliptic varieties, why ellipticity is interesting. So it gives a really very big restriction, very important restriction on the variety. So theorem, a recent theorem by Kusakabe says that if X is a smooth algebraic variety, and X tilde is the universal cover of X, then the fundamental group is finite of X, and the universal covering is an elliptic algebraic variety. So the ellipticity comes to the universal covering. In the algebraic category, we have a strong analog of theorem B, and this belongs to Forsnerich. Let X be a smooth algebraic variety and D a bounded convex domain in Cn. And X is supposed to be elliptic. Then any holomorphic map in a neighborhood of the closure of this domain to X can be approximated by morphisms, by regular maps of Cn to X. So in the original setting, in complex setting, there were entire maps, and now there are morphisms. Now, there is a theorem started by Forsnerich and finished by Kusakabe, which says the following: take a smooth algebraic variety and assume that it is elliptic. Then there is a surjection, I mean a surjective morphism from Cn capital to X. Moreover, you can choose this so that if you delete the branching locus of this morphism, where their rank of differential drops, then on this domain, the restriction is still surjective. This open subdomain of Cn still surjects onto X. And this is very, very useful. If X is complete, then you can replace n capital by small n, which is the dimension of X. This is Forsnerich. If X is not necessarily complete, then you can take, instead of n capital, you can take n plus 1 always. And I have to note that the Forsnerish proof is really a proof using the tools of complex analysis. Why the Kusakabe proof is different and purely algebraic. Therefore, it works for any algebraically closed field of characteristic 0. Corollary, which uses some remark of Kusakabe and proven with together with Kaliman. So if X is elliptic, then the endomorphism model semigroup of endomorphisms X M transitively on X for any M. What does it mean? That means that if you take any two ordered finite set of points in X of the same cardinality, then you can find an endomorphism of X sending the first set to the second, respecting the order. An analog was known for flexible varieties, where even the automorphism group X M transitively for any M, and here also for any M. Okay. So the flexibility is more stronger condition than ellipticity, and then the conclusion also stronger. So I see that now is 3:30. We started a little bit later, but maybe the next speaker will wait. I don't know. So it's up to you to decide whether I continue a little bit and how much time, or I stop. What is the answer? Do you hear me?
Yes, yes.
Mm-hmm. So what
You have 1 minute or 2 minutes.
1
so
or 2?
can...
Okay. So then another maybe couple of slides. You see that all this Gromov theory, it implies the notion elaborated especially for this case. But in the algebraic geometry, there are notion of rational variety, uniformly rational, unirational, and the questions which were posed already in the Gromov paper, whether you can formulate ellipticity in terms of these notions. So any elliptic variety is unirational, not necessarily rational. For surfaces, this is the same by Leroy's theorem. Starting with dimension 3, these two notions are different, and therefore there are two questions of Gromov. Is every rational variety uniformly rational? What does it mean uniformly rational? That means that any point of variety has as a risky open neighborhood which comes from as an open set in Cn, in some Cn. So, this is an open problem. It appears already in this paper. And the second question is every smooth, complete unirational variety, elliptic. So ellipticity implies unirationality, whether the converse is true. So both problems are widely open. And I finish with this theorem, which is written here and very recent. And so with Arjantsev and Kaliman, we proved the following. If you have a uniformly rational complete variety, then it is elliptic. For non-complete, this is not true. Fourth, uniform rationality implies ellipticity. And the second, if you have a unirational smooth complete variety of dimension n, then it admits a surjective morphism. And this actually gives a characterization of new characterization of unirationality. A variety, complete variety is unirational if and only if there is a surjective morphism from the affine space. I finished. Thank you for attention.
Thank you very much.